All right. I said we get started.
Alrighty. Thank you all
right.
for coming out to this fall's L3Harris and Florida Tech Talk. I'd like to welcome organizations, members of SWE, NSB, SHIFI, and IEEE. Very glad you guys can join us. Thank you as well to Donna and Susan at Career Services for helping us set this up. Today, we're very lucky to have Bayardo Payan, Senior Engineering Manager of the Microelectronics Department here at L3Harris. Bayardo is a fellow Florida Tech Panther and started as an entry-level engineer and moved all the way up the ladder to Senior Engineering Manager. I know I'm excited to hear his presentation, so without further ado, take it away, Bayardo.
Awesome. Well, thank you so much, everyone, for having me, and thank you so much for taking time to listen to a fellow Panther, man. So I'm a bit of an old school guy, but I definitely remember having fond memories of FIT, and hopefully you'll get some good kind of feelings of where your career could possibly head. I know I've had a very joyous 20 years here at L3Harris, and I kind of wanted to delve into that, why I've been here so long. I mean, there's a big reason for it. So let's get started. By the way, if you guys have any questions, again, feel free to ask at any time. So again, just a quick background on who I am. Bayardo Payan, native Floridian, so grew up in Jacksonville, went to school in Orlando. I received my undergraduate degree in Bachelor's of Electrical Engineering. I really focused on, at the time, semiconductor fabrication and electronic materials. So what I've got in the presentation is kind of a breakdown of what electrical engineer, like, you know, it's when you start thinking about it, it's such a broad, even though we are specialized electrical engineers, it's such a broad career area. So I want to kind of tell the story of where my drive was, where my interests were, and how those led to some of the opportunities that I was able to take on. So again, bachelor's back in 2003 from UCF. I actually started Harris. I was just telling the story. I graduated on a Saturday from UCF. I packed all my things and I moved to Melbourne, which I had never heard of, even though I lived, right here, on a Sunday. And I moved into my apartment Sunday, and I went to work for the very first time at L3Harris Corporation on Monday. And it was a day I genuinely will never forget. It was a wonderful day. Lots of things coming at me, eager engineer, ready to go and take on the world and solve some really hard problems and get really excited about being into a lab. At the exact same time as I started L3Harris, I knew I wanted to continue my education. I've always been a huge fan of learning. That's one of my core drivers. That's, as you'll see, I'm sure that's one of y'all's core drivers as well, is we love folks who want to continue learning. We love folks who want to continue expanding. Just because you're done with your university and formal education, I mean, I know you've heard it so many times, but learning is such a lifetime skill that we want to harness. We want to make sure we culture that into our folks. So immediately as I started L3Harris, yep, I'm ready for the workforce, but I want to keep going. And I was able to do that within L3Harris. They were able to, we have a very good higher education compensation benefit that we get. So being an employee, I was able to get my tuition and a lot of the fees, if not all of it, pretty much for free, going to FIT. So I started at FIT literally 3 months. I think I started the winter semester after I started Harris. And within FIT, I had already joined at Harris, the microelectronics department, and I wanted to continue to delve in that. So I got my master's in electrical engineering from FIT in semiconductor device physics. And as I was saying a bit earlier, one of the just wonderful memories that I have of FIT was the fact that the professors that were teaching me these advanced courses, these advanced degrees, mathematics, and specifically in my case, clean room operations, silicon fabrication, how we actually do die, how we do digital signal processing. These are all my areas of interest. Were not only folks that had their PhDs in academia and had a resounding history of publications and research, but they were also folks who had been working in the area. They'd worked at Harris, at Northrop, at Intercell. They worked in these fields. and as you'll see as you enter your career in your career field, it is a bit of a shock to go from academia into a world where you're kind of now free to make your own path. One of the biggest eye openers and key things that I like to make sure that we tell new college grads, and I still feel it and I still remember in college, it was wonderful. I want to be an electrical engineer. Here's my syllabus. Here's all the things I get to do, and I see the end goal. And if I check these boxes, I get what I want in the end result. When you start at a company, I will say that your career is in your hands, and your peers and your leads are there to help you achieve those goals. But those goals need to come from your initiative. And I think that's one of the most shocking things that I'm sure this is the first time you hear it, but to me, it really resonates with me of when I started Harris and I said, all right, let's go. Let's start solving equations. Let's start. And then I'm sitting here going, well, how come I'm not doing all the things that I wanted to do? So it was a bit of a shock, but with time, as you'll see here, I got to experience what I would say a really, really fulfilling and successful wide breadth of a career field. So where I'm at Harris, again, I've been here about 20 years. I started here in 2003 as a level 1 engineer, electrical. I actually started within the department that I'm currently the engineering manager for. So not only have I been with Harris for that amount of time, I've been with the department. I've grown up with a lot of the folks that we've had here for the last 20 years of my life. And I've learned a significant amount of engineering technology from these peers. So I'll get into the details of what kind of makes our department unique within L3Harris. You know, I keep mentioning microelectronics over and over again. That has multiple definitions to many people. So, and within L3Harris, that's what I'll show some examples of what we've done here. All right. So let me move on to the next slide. So I haven't been to campus in quite some time, probably in the last 10 years or so, but I've heard we've got L3Harris names all over the place. So you guys are probably familiar with what L3Harris is about. If not, here's just a quick spiel that I wanted to put up there. And the reason I put this up there is, we are a government contract, primarily government contracts company. We do commercial work. We do things that you may not be aware of. I know I wasn't until I became highly integrated with the company. But one thing that really strikes me as something that I think is a key positive is the fact that we have platforms, electronic, mechanical, and material platforms that take all disciplines of engineering in literally air, land, sea, and space. So in every single aspect, environmental aspect, we've got either products or solutions that we've created for our customers that are utilized, again, in areas that you wouldn't believe. Starting with the sea, let me just make a couple of comments. My personal career, I have focused probably half of my career working on maritime systems is what we call it here. So it always starts with secured communications. One of the key technology drivers that we provide for our customers is the ability to, be able to assure that a message or video or real-time data is securely encrypted and securely received between two parties or multiple parties, and your adversary has a very difficult, if not impossible, time intercepting or canceling that communication. So that is an incredibly kind of a tenet of what L3Harris really stands for. Assured, secured communications was one of kind of our themes that we continue to grow on. But in that area, unmanned vehicles is there was a huge explosion of unmanned vehicles, not ROVs, which are remote operated, but AUVs, drones, all of that. You guys probably were born into that age. In the early 2000s, these types of systems were at the forefront of the technology. And now we're seeing, the early steps of that development phase actually being fielded into systems that are now being operated by our military and our partners and our, law enforcement folks to actual use cases where you don't want to put anyone in harm's way. So with that comes extreme amounts of electrical, mechanical, material, systems engineering efforts that go into it. And that applies, and again, I focused on the sea. That is literally 10 years of my career. Terrestrial systems, I have had a couple of opportunities to work on terrestrial systems. Again, data collection systems of environmental metrics, either in a war environment, battlefield, or just monitoring stations. Harris isn't all defense. We do delve in areas of the commercial land in terms of supporting scientific exploration. We've been part of all of the space telescopes that have gone up in space, all the, the recent hurricane that we have, the NOAA imaging satellite systems, which are called GOES-R systems. If you ever go to NOAA.gov and you pull up an image link and a satellite scan of Earth, those systems were co-developed with Harris technology in mind. And that's what's covering. I'm kind of jumping over to the space area. And lastly, air. Again, a continuation of secure communications and unmanned vehicles, where we're actually creating unmanned vehicles for our warfighter, but also manned vehicles. The F-15, F-18, a lot of our fighters, the F-35, these are all fighting systems that are now evolved into literal flying computers. We're creating high-speed data links between these systems to have as much information as possible being collected and presented for the warfighter to be able to respond in real time. So all of these things I'm talking about are just hey, what does Harris do? A little bit of everything. And depending on your interests, I know mine, and I'll go back to it. I thought I wanted to be an Intel chip designer, like I want to work in silicon, until I got a feeling and a taste of doing a little bit of everything. And it really opened up my eyes to, gosh, there's so much complexity into the smallest things that we take for granted. So let me continue talking about what we'll be discussing here. This is an internal image of what we do at L3Harris with our engineering, with our engineers, essentially. The majority of the workforce, as you can imagine, is engineering. We are here to solve technical problems for our customers. So engineers kind of can take two paths within L3Harris. What I've highlighted on the right is what we call our career framework. Starting at the very top, you've got executive leadership. Most of those folks are engineering by education, senior vice presidents and presidents of business areas, vice presidents and senior directors of actual either business areas or disciplines. Electrical engineering, we have senior directors and vice presidents for that. Mechanical engineering, software engineering, material science, physicists, systems engineering. I mean, the list goes on in terms of actual education and the kind of leadership roles that you can take on. But what I really wanted to focus on today, because my passion has been under the leadership and management professional areas. You see that red arrow that's pointing up. Starting with associate, senior associate, specialist. These are titles that we use here. They have corresponding levels. Those are technical engineering titles. So that is the technical path, and the ultimate technical accomplishment for an engineer here at Harris would be a level 7 who is a senior scientist. And a senior scientist is literally driving ungodly amounts of technically difficult, challenging solutions to our customers. They are presenting to United States Congress, they are presenting to senators, they are presenting to admirals, they are coming up and solving problems that we are very good at solving, problems that others just cannot do that. So a senior scientist is someone who is has had a significant impact, not only for the business, but really just the technology that they've brought in that have allowed us to target some of these business areas. That's the ultimate goal from a technical peak career. And a question that I know in this role that I'm in, I get asked a lot, is it better to be a manager, better to be technical? It really depends. I mean, you can succeed and be compensated very comparably. A senior engineer, senior scientist, likely makes more than some of the executives that you've got up there, the VPs and presidents, because they have the thought, the intellectual property, and the influence from the technical community to drive and bring in significant amount of business. So let me just make that statement, because that I think is, everybody thinks, oh, I need to be manager, I need to be director. No, absolutely not. If you want to be a lab rat, which is what I love being, there's a clear path for you to not only be an individual contributor, to not only start off and start learning and honing your skills, but to become an absolute industry expert. And I kid you not, when I'm talking, these folks do interact with our highest levels of government and our highest levels. They are guiding our CEOs and other CEOs onto where we should be taking our technology next. So that's what I'm going to focus on this afternoon, because that's been my career path. I've always had that dream as a child. I always wanted to wear a lab coat. And that was honestly the only reason I took this job. Not the only, but that was a big key reason.
Cool lab coats.
It's cool lab coats. I love the idea of being a scientist. I love the idea of coming to work and not having an answer, and having our leaders looking at us and saying, hey, our customers have this serious problem to solve. Have fun. And it's the best. And it's the freedom that you get to go explore, use your creativity, use your imagination, use your connections that you've made with not just your discipline, but with the other disciplines. I'll show you how that all comes together to solve really complex problems. So a little bit digging more into engineering. So we spoke earlier about the managerial path and the difference between that and executives, as well as the scientist path, which again, a senior scientist is the ultimate accomplishment one can have in a technical career. So what I wanted to highlight here is we have what we call, these are sub-disciplines within engineering. So aeronautical engineers, electrical engineers, engineering management is kind of dimmed out. Don't worry about that one. It's not technical, but image science engineer, information security engineer, cybersecurity. I won't go through the list, but as you can see, these are what L3Harris would consider buckets of engineering talent that we hire for. That doesn't necessarily translate directly to a particular degree that you may be getting. You'll see up there, you don't see physicists. I will tell you that some of my greatest peer mentors are pure physicists. And in fact, we have a chemical engineer right next to us.
Working as an electrical engineer.
Working and identified as an electrical engineer. So, and again, our department is in a unique situation because our department's goal within L3Harris is taking a system and looking at it from all of these disciplines: electrical, mechanical, software, firmware, chemical, materials, and figuring out how to make it smaller, how to make it more capable, and how to make it survive environments that typically you wouldn't think of electronics being able to survive. So I guess what I wanted to show up with this slide is, if you don't see your career path, or I'm sorry, your degree up there, that doesn't mean you're not a very useful contributor to L3Harris, like whatsoever. It just means that Harris, this is just how we categorize our engineers. That's all I wanted to mention here. All right. So let me start breaking into, again, what I want to talk about, what I get excited to talk about, electronics. I've got kind of a quick example of what I would consider in my career and what I've seen within L3Harris, sub-disciplines of what an electrical engineer comes out of school. Again, I came out of school with a general electrical engineering degree. a little bit of specialization in semiconductor fabrication. I really wanted to go work for Intel or AMD or NVIDIA. I really wanted to go create die. And really what I enjoyed the most when I was in college was physically taking silicon and the ingot, even before the ingot, you've got this stuff laying around in our beach. How the hell does sand turn into some of the most capable processing systems that we get? So that conversion, that physicality of this ubiquitous material becoming such a critical part of our everyday life that we take for granted, our cell phones, our cars, all, I'm sure you're all are aware of the chip shortage. So I'm just fascinated by the material aspects of electrical engineering. And, I took my circuits class, and I'm ashamed to say it, but that was my first B in engineering. And let me jump to the end a little bit. I am really good at circuits now, and it's kind of been my thing. And I've designed a significant number of very complex architectural electronic systems, satellite systems, very, very complex communication, encrypted systems, large server systems that have been custom designed. So if you would have asked me back in college, hey, Bayardo, do you want to do these types of electronics? I said, absolutely not. No, I want to go play with sand. I want to go make silicon. I want to go dope some PNN junctions. I want to go make some transistors. So that's how I started. But within L3Harris electrical engineering, what we do is we kind of look at what your interests are. I would be categorized, I've got these kind of sub-bullets in there. I've had the opportunity to kind of play in all of those areas. I told you my interests were very much into materials, but my career has put me in positions where I've had to be a digital hardware designer, a digital hardware engineer. And what I wanted to do was to share with you, what does that really mean? What is it that, back to that transition from school. At school, you get that great syllabus. You have a true understanding of what it is that you need to do to exceed and succeed in your class. At work, it's a little bit more blurry. We have a big task, we have a big program, and we are given as new college grad engineers or as new career engineers, we're given a very, not a small piece, but a manageable piece of what we can do to design. And it's what I try to do is I try to remind everyone, hey, this cog fits into a much larger, much complex system. But when I go and design something, I don't know if you guys have all gone through your senior design phases or are working through that. I'm sure if you're working through it, you're probably learning all of the issues that come with working on a team and getting something to work the first time. If you haven't, you're going to have a lot of fun working on a multidisciplinary team. So you're not working on your own. Engineering is a team sport. So I keep side skipping all of my bullets, but let me get back to it. Digital hardware engineer. Well, what does that mean? A digital hardware engineer is, again, probably what I would associate my career has followed the most. It's someone who understands microcontrollers, microprocessing units, computing systems. I can take an FPGA up there. So I've got a couple acronyms up there. A to D's, D to A's, point of load, power distribution systems, high-speed timing, high-speed serial links. And I can actually physically, so what does that mean? Well, I can build a computer. I can go and build an electronics physical card. I can build, you guys have all seen teardowns of our phones. I understand what typical industry interconnects are between an FPGA, a DSP chip, a microcontroller. I know what it takes to connect those. I know the issues that come with connecting those when you have high-speed digital signaling, serial links. There's very physical and real effects when you actually build this. Everything looks fantastic on simulation and on paper, but when you start putting these things together, you have to take into consideration material properties of what you're building. You have to take into consideration shielding effects of how you're radiating, how you're actually creating your board, how you're going to be placing your components. If I've got something that needs particular power requirement located here, and I'm placing my power component, several inches away from from the load, you're going to get a voltage drop. It's not an ideal system anymore like we had in school, where we didn't have to take into considerations the physicalities of something that actually gets built.
And designing all this to the highest reliability standards as well, right?
Absolutely. Yeah, no, as you
Entire industry.
as you saw earlier, these are systems that, and my career specifically, and a lot of the work that we do, these are systems that get deployed into areas that we don't easily have access to. Space systems, they're intended to last for several decades. These unmanned maritime systems, they're literally at the bottom of the ocean. And it is a significant effort, and from a technology and a money to go and address issues. So they're high reliability, they're very, very custom electronics is what I would say a digital hardware engineer does. So moving down to the next sub-bullet there, firmware engineers. Some of you may be focusing on FPGA specific studies. That's what we call firmware design here. Obviously, that is still an electrical engineer. You took a significant number of classes with respect to, RLC circuits, with respect to EM waveforms, DSP, but you're more interested in going into what's called a field programmable gate array. And what you see on the right there is actually a Xilinx FPGA development kit. And the reason I'm showing you this is this is pretty representative of some of the systems and capabilities that we integrate on a very regular basis for, the land, air, and sea blocks that I showed you earlier. So anywho, what's an FPGA designer? It's someone who will work very closely with the hardware engineer, the person who's building the circuit card, and say, Bayardo, these are the types of algorithms that we'll be placing in the FPGA. These are the resources that we'll be utilizing. We're working together and saying, how much power are you going to be consuming? How many of these GPIO are going to be high speed and sensitive and critical GPIO that I need to make sure that I route correctly onto the board? How much memory are you going to be consuming so we can attach enough, DDR4, or maybe we can't have DDR4 because I have to go now, the fourth bullet down, power and analog engineer. I have a power budget. I have a limited resource of energy because this is going to be an unmanned system that's running off battery. So there's all kinds of analysis and interactions just within electrical engineers alone. They're having to work together to create something that looks like what's on your screen right now. Moving down to RF and antenna engineer, that's another subspecialization that we've got. And when I say subspecializations, I'm talking we have entire departments within L3Harris. And a department is approximately 70 to 100 engineers dedicated to these specializations. We have departments dedicated to digital hardware engineering, departments dedicated to firmware development, departments dedicated to RF and antenna engineering. So RF and antenna engineering, RF, obvious, radio frequency transmissions. If you want to talk wirelessly, you're messing with RS, you're going in there and you're learning not only how to create an RF transmit receive system from a physical point of view, but you're learning how the two links between free space, you're no longer in free space loss, right? There are real issues when you're trying to deploy a communication system, whether you're in a forest, whether you're in a desert, or you've got significant obstructions of in a city. I'm sure you're hearing of 5G, the latest work that's going on with the rolling out of the higher data rate of cell phone utilization. That challenge, Harris has a little bit of a play into that. We've got some simulation capabilities that we're helping out with actually some of the commercial companies, T-Mobile and Verizon and AT&T, to help distribute and identify locations for them to have as much coverage, because everybody wants as much coverage as possible. But you got to remember, these are very expensive computing systems that we're putting up. So you want to minimize the cost of it, but you want to make sure that you have the coverage and you want to take into account any obstacles you've got in the way. Back to something that's more relatable to my career. I've not delved too much in the commercial, but for a defense communication system, when you're creating a battlefield network, you have to take into account any losses that you may have in the atmosphere. If you're talking to space satellites, there are a lot of simulation tools that you have to take into account, and you have to design and preemptively assume all of these no longer, I remember when I took statics, everything was frictionless until reality hits you. And yeah, friction exists. Losses, parasitic impedances, parasitic elements to electronic circuits, they're real. And they will burn you. And they have burned me many a times. And there are lessons that I've learned throughout my career. So back to RF and antenna engineers. Those are my friends who go off and have a really good time playing with radar systems, software-defined radio systems, and they're playing anywhere from hundreds of megahertz. Some of the common bands are 434 megahertz, which is a low RANS band. There's a 900 megahertz band that's used for communication, and then you've got GPS, which you start getting into L band. GPS and low frequency SATCOM communication is what L band is. Then moving on to X band, which covers what I would say imaging satellites. As we were talking about the pictures you see of the hurricane, when you go to Google Maps and you're able to zoom into street views and all that from satellite imagery. Those are now operating at higher frequencies at approximately X band. So are radar systems. Then you get into what I would consider millimeter wave, but the industry considers millimeter wave frequencies, which are in the order of 20 gigahertz all the way up to, I've got 40 gigahertz here just because that's kind of where I've stopped my lessons here, but I know of systems that operate up to 80 gigahertz of RF bandwidth. And when you're dealing with such a high frequency, again, all those things that we talked about that you could ignore for, Wi-Fi is 2.4 gigahertz, something that's operating at, orders of magnitude above that. It's much more difficult to pay attention to the close details of physically creating the antenna, physically placing your components, physically worrying about noise being created by your power supply. All of that's just going to create just issues that are unexpected at these very high frequencies. So that's where our RF and antenna engineers kind of focus on. And I will say of all the subdisciplines that we've got up here, a lot of the time they spend is in a tool called HFSS or ANSYS, where they're doing significant amount of simulation in terms of free space losses and radio field propagations. That before they're able to go and do a lot of prototype work, they have to understand how these things are going to behave at these frequencies. So fourth now, power and analog engineers. Again, another area that these are specializations, but it doesn't mean that's all you get to do. And I'm jumping ahead, but I've had a chance to work in all these areas and I learned so much from all of these areas. Power and analog engineers it doesn't sound sexy. It doesn't sound exciting, but I will show you cases that they're necessary. Everything absolutely needs power conditioning. That FPGA that you see in the middle, that large chip, which is the zinc in that image, that has 28 individually controlled and has to be sequenced when you power this thing on. 28 individually controlled voltage regulators. I mean, let me just let that sink in. It's like, yeah, you see the top, it's got 12 volts coming in. Awesome. Now, it's running a significant number of sub voltages that need to be isolated from each other in order just for that chip to turn on. So power and analog engineering are another area that, in my opinion, the more you dig, on surface, you're like, yeah, that sounds easy. No, there is a significant amount of effort that goes into each and every one of these subdisciplines. So yeah, power conditioning, power distribution, power analysis, actually, again, not trying to create a lot of switching noise, power conversion noise into your system is very critical for the things that we do. Lastly, and this is the area I've worked least in, but it was again my really big dream that I wanted to work on. And I'm happy that I had a chance to work in all of these. We do have semiconductor engineers, actually within our department. We have the ability to go into our clean rooms. We have an on-site clean room, a class 1000, class 10,000 clean room that is developing a lot of future processes in research and development. Let me make a quick clarification. We're not in the business of making GPUs or CPUs. We're not making transistors. We're not making die. What we're doing is we're taking the technologies and the lithography and all the techniques that the Intels and AMDs and Texas Instruments are utilizing. And what we're trying to do is, you see the green motherboard back there, that's your card. We're trying to use silicon as the next level, and that's emerging technology of interconnection between devices. And I guess what I'm trying to get at is the advantage of using silicon is you can create significantly smaller footprints, tighter signals, tighter lines. You can cram more into a silicon substrate than we currently can with organic substrates that you see up there. The other fun thing that we do get to develop here is MEMS. If you all are familiar, if have been exposed to the microelectromechanical systems, we have a couple of programs that we support currently and that we've developed and homegrown in-house that are literally a 2.5-inch stick of gum. It looks like under a microscope, you now zoom in at the micron levels, probably, I want to say these are about 20 some odd micron thick. And these are digitized fingers that we can position with 10 nanometer accuracy to push and pull against surfaces. So that's some really neat applications there. And I will say one of the kind of not sad, it is a little sad. One of the saddest things that I've had in my career, as you can see here, I'm showing you something that you can find on the internet. A lot of the work that we develop, as I mentioned earlier, especially in our area, is focused towards defense, is focused towards other missions that we really don't get a chance to show off and share with folks. So I'm using exemplar systems. I'd love to show you some of the things and applications I've worked on. And that's kind of the one thing, if I were to go back, that I wish I could share a bit more in detail, which is why I get super excited when I get to talk to Reed behind the vaults and closed doors and say, look at what we're doing, isn't this amazing? And then we walk out and pretend nothing's happening. So that is kind of an oddity in this particular career field that I chose. All right. So let me get into kind of what I've been leading to this whole time. I'm going to walk from the left and walk to the right. So as I mentioned earlier, I started as an electrical engineer. I genuinely just wanted to do research and development. My ideal job at the time was, I don't want to design circuits. I don't want to code. I want to go and be in the lab, and I want to be the mad scientist mixing chemicals, building something, seeing it blow up in my face. I love that idea. And I was able to communicate that. And this is again, back to having that syllabus. One of the things that we encourage our new college grads and our early career individuals is to, speak your mind. Tell us what you're interested in. Tell us what you want. And, between the ability of work and between your leads and your team members, we can start pointing you towards what you want, but it needs to come from that person. So it took me a bit to learn that. And once I started being open of, put me in the lab. I want to start probing things. I don't even care what it's for. I worked under a metrology area for the first couple months where I would just do inspection using scanning electron microscopy. I don't know about you guys, but there's not many people that can run a scanning electron microscope. And that was one of the first things that I got to do as a new hire, as an electrical engineer. I also got to develop and work actually where Rita's working. I used to work in the area where we did PCB fabrication and create some of our PCB boards and work with really unique substrates. And I got to learn how to physically make a circuit board in my hand. And I loved it because it was so different and so exciting and so new from anything else that I had learned in school. But I would say the first 2 years of my career were heavily focused within the microelectronics department, working in our labs. And the highlights when I was putting this together, we had great opportunities to work on patentable ideas. So at this point, we're developing intellectual property for L3Harris. And I wanted to put a picture up, but these are again from the internet. These are the actual images that we created. And it, in retrospect, it seems so simple, but it really was 2 years, a year and a half of my career coming up with an idea to embed, in this case, transformers and inductors. At the time, this is back in 03, even today, actually, most power supplies did not have integrated components. You would get a FET controller, which then sends pulses to charge a capacitor in an inducting system. That's how a typical switching regulator works. And these inductors are large storage energies of magnetic fields. And you've got these large capacitors that, are physically large. And what we were doing is taking the largest component in these power supplies, which was the inductor, as you can see over on the, I'm going to turn on my little highlight here. This is probably the size of your thumbnail, this square here. And what you can see is this is an embedded inductor. It's actually a transformer, an embedded transformer that we built into a multi-PCB layer stack up.
That's awesome.
And the reason for that, it was pretty cool. No one had ever thought of this. And the reason for that is we now were able to create pads, and pads are electronic connections to put chips down. I could put additional capacitors on top of this inductor. I could put additional chips on top of that inductor, and I could use that same inductor that served as my motherboard to be a completely integrated system. So that's what that first bullet is, integrated at 12 volt to 3.3 volt. It was a 2 amp switching regulator. And this was a circuit at the time that's probably 1 square inch that we miniaturized and created a 3-dimensional system of it, and something that was the area of your thumbnail. So that was like, you're talking now, what is that? A reduction. I want to say it was, yeah. So that is a great keyword that we use here all the time. You'll likely hear it, low swap. SWAP stands for size, weight, and power. And that is kind of the ethos of what we do in microelectronics, to try and make things as small as possible, low power as possible, lightweight as possible, but also, and that's the gotcha. Here comes the gotcha. I want it better. I want it faster. I want more memory. Everybody wants that. And obviously the phone industry has been one of the commercial leaders in that area. So the other kind of notable thing that, as I was putting this together, was this DARPA project that I also had a hand in helping. And again, the first one, cool. I was an electrical engineer. I was doing some really fun permeability equations and calculating how many lines we would need to get the inductor Q values. And it was a lot of fun MATLAB simulations. So I felt like an electrical engineer. The second one was completely out of my league, and I shouldn't have been doing it, but it was great. It was a material science. Let me back up. This is a study on creating a MEMS device. UC Berkeley had created a rotary engine. I don't know if you're familiar. It's literally an internal combustion engine, but instead of cylinders, it's called a Wankel rotary engine. In fact, the Mazda RX-6s and RX-8 sports cars, they use a rotary engine. So feel free to Google that, because I had to when I first worked this. I go, wait, what? let me back up. What they're looking for is, again, trying to help our war fighters. At this point in time, lithium ion batteries were just coming on board, but the majority of the battery systems that, our military and service people were wearing were these large, heavy lead acid batteries. I don't know if you're aware, but the energy density for batteries with respect to energy density of hydrocarbons, gasoline or any other hydrocarbon fuel, it's orders of like hundreds of times more energy in it. So the idea here was to create that same form factor of a battery, but that battery would now be literally a little liquid gasoline, liquid kerosene container that ran one of these engines that would then act as a miniature, and we just had a hurricane, so you guys are probably familiar with generators, a miniature generator. We were creating, you would put in gas, it would run this internal combustion engine. The internal combustion engine would run a magnetic generator that would create 12 volts and whatever amperage we wanted to output. It was awesome. It was just DARPA is if you guys get a chance to work with any of our national labs, Army research labs, Navy research labs, they are just the funnest. You want to be a mad scientist, these guys have the best kind of work. And the cool thing about L3Harris is we work very closely with them when it comes to these next generation developments. So that PowerPoint down there was just a very interesting. The Harris part of it was the packaging portion. So we were given this very boy, I forget what it was, something reactive ion etching, this MEMS device. And we were given it, and what we were told is, okay, great, we've got a MEMS device that works on silicon. How do we really get it into something that's a form factor that I can take, rattle, roll, will survive the elements? And we created a packaging method as well as a control card. You can see there's a circuit card that I helped design there that would create and control the motor. Because the motor can't just spin. You needed control systems that come into play. You needed, obviously, the generator part. You need to be able to store that energy in capacitors. It was just another really fun program that opened my eyes to outside of electronics. This was my first experience of, wow, this is a large system.
Yeah, I mean, just in that PowerPoint, you get material science, some mechanical engineering, right? Probably
Bingo.
Model that rotary engine, photolithography.
To go create it, yeah.
Create it, manufacturing engineering, and that electrical engineering to design your circuit card, microfluidics mock-up, so some thermo or some more scientific theoretical side of things, covering very many disciplines just in one project. That's really cool.
No, it was, and to highlight Reed's comment, in our department, I showed that list of power, FPGA. There are departments dedicated to that. One thing I haven't said, but I'll say it now and kind of spoil it, is microelectronics department is in a unique position where we are comprised of pretty much any engineering discipline you can think of. We have the physicists, we have chemists, PhD physicists, chemical engineers, material scientists, electrical engineers, mechanical packaging engineers. We do have some firmware and software embedded programming engineers as well. And we also have very specialized non-engineering, but technicians that can go and create and go into our labs and make some of these test articles for us. So, Mike, that's why I haven't left this department. It is just so broad. And if I want to pivot from, I'm getting bored with designing microchips.
Go to the next lab over.
Let me go talk to Reed. Reed, what are you guys up to? And then I you know what? That sounds like not only am I getting bored, but maybe I learned something that I didn't know about that I can take back to my program and say, we have a capability that we can combine two completely different, if you're in a siloed only working with electricals, you forget about these other system things that come into play to deliver a real system. The mechanical folks need to be involved. The thermal folks need to be involved. The structural folks need to be involved. So we have that kind of organically within our department. And that's truly what I love about our department. Moving to the top right, as my career progressed, anecdotally, it was a funny story. I was having a lot of fun on the left, getting patents, playing in the lab. No, like if it didn't work, it's okay. It's research. And we learned something. It was always you learn something. Even when things fail, you learn why they fail. We change it. It was fantastic. Um, but then reality set in, and my manager, I think, remembered that I was an electrical engineer. He goes, "Hey, Bayardo, you're electrical. You want to do a circuit?" And in my head, I'm like, "Absolutely not. No, I'm having like, give me the white lab coat. I'm having a blast." I didn't say that, and I said, "Sir, yes, sir. I'll do whatever you tell me." But I'm glad I did it. I again, I did not want to do circuits. I cannot stress that enough to you, but I did it. I some of the first things that I got to work on were what back in the day it was very upfront new coming technology, radios, software defined radios. But what does that mean? That means I can put a programmable waveform, and I can change the waveform on the fly. Again, back to that secure communication link. If this particular frequency or this particular modulation scheme or waveform is being jammed by an adversary, I've got a different one. If that one gets jammed, I've got a different one. I'm switching the complete the complete parameters of that communication link in real time with an electronic system. So I got to work on some Department of Defense handheld and unmanned vehicle. At this time, we were doing lots of AUV work, reconnaissance work, radios. And my job, I've got a picture of a circuit card down here. My job again was the digital designer. Go identify a microcontroller. Go identify a storage for memory, flash memory storage, whether it's an SD card, whether it's NOR flash. Go identify how much RAM we need. Go do the calculations for the kinds of things. Working with the customer says, I want a link and I want a communication that transmits this much data over such amount of time. And my job is to translate that into how do I build that? Does that exist currently? Do I need to go build that? And we start what we call our trades. Do I need to go build this? What kind of options are available to me? And then we start a detailed design of here's what we think will solve your problem, Mr. Customer. And it's a very great hands-on back and forth. Not only am I talking to our customer for what to solve, but I'm also, again, as going back to this multidiscipline interaction, I can't just give them that circuit card that you've got highlighted, that I've got highlighted there. No, they're looking for, imagine Samsung just giving you like a bunch of chips. Like, no, it needs to be ergonomic. It needs to be user-friendly. So all of that started to come into play in my mind when I was making design decisions in that area. At the exact same time, well, not the exact same time, but around that time frame, while I had become very good at making these types of circuit cards, we did start working on some really neat, and again, back in the day, 2005, flexible electronics. Specifically, what I don't have images of here is wearable electronics. Again, targeting warfighter ability to, instead of carry a big radio on them, literally having almost an RFID built into their lapel, built into their fabric. We were doing lots of research and development into using inkjet printers to print silver and conductive ink, and using lathing techniques and silicon die thinning techniques to get very, very, very thin microcontrollers, memory chips that were not quite flexible, but could withstand some flexure. So I've got an image here from Georgia Tech. They continue to do that work. They're actually a very cool lab that we still work with in terms of flexible electronics. But that part of my career had to do even more so when I talk about embedded flexible electronics. Again, I can't just go design that card on the left. I now am working with the system engineer. I'm now working with, and also obviously the firmware and the software and material and mechanical engineers, but I'm working with the packaging engineer that says, Bayardo, it's got to go in a pocket. Dude, that antenna is not going to fit. It can't be rigid because it's going to hurt somebody. It's got to be ergonomic. So all of these other things start coming into play. And in the back of my mind, I'm like, Yeah, I don't remember taking a class in my electrical engineering that talked about how to put things into, your lapel or your pocket. So really fun learning experiences again. Lastly, on the right, I think most everyone, and these are now becoming pretty ubiquitous. Apple AirTags. 10, 15 years ago, we were utilizing these devices. Not They're not the same technology as Apple AirTag. Apple AirTag uses Bluetooth and talks to nearby iPhones. They've created a mesh network of the thousands of iPhones, millions of iPhones that they've got. What I got to work on were programs again for our defense industry that could be used for the tracking, what's called TTL, tagging, tracking, and location sensors. A lot of it was based off GPS or UHF systems. So back to working with RF engineers, back to working with signal processing and FPGA custom waveform folks. And I learned a significant amount of SATCOM communication. This was kind of my first introduction into I don't know if you got how much in depth you're aware of how GPS works, but it's freaking amazing. As you can imagine, anything that we take for granted, as soon as you start scratching that surface, it is unbelievable the amount of effort and engineering that goes into the everyday things that we use in our lives. And having been a part of some of that development work is just it's very pride filling. And I feel just really happy to have just been around some of the very, very, very smart folks that got to develop some of this work. So I would say then moving into 2010 and 2021, so the last 10 years of my career, I went from what I would call a level 1, level 2, level 3 engineer. Level 1, level 2, level 3 engineer are engineers who are learning the craft, learning the process, because each company has its own process on how to develop particular products. And I'm given kind of, here's a card, go design it, Bayardo. Here's a module, can you come up with an idea? And everything's kind of really clean and cut, and I can see the whole system. In 2010, I got an opportunity to work on a very complex communication maritime system, that government communication and data capture system. And what that really was, as an example, you have a Navy carrier fleet that's out in the ocean. That's usually comprised of a US carrier and literally 10 to 20 or 30 additional support ships with hundreds of other airplanes. Imagine how they communicate out in the ocean. I got to work on a system that enhanced that communication. So what I'm showing here are some examples of what I got to develop. And again, it's hard to discuss. Obviously, the application was sensitive. The actual system, these are not, except the one on the right, these are not systems, but these are representative things that I got to do. I went from these small, very purpose-built devices into a larger, how do you handle hundreds of gigabytes of data communications per second? How do you store this information? Oh, let me hit on that. When I'm showing this image on this Curtis, right, that is a transceiver CCA. It's got 3 FPGAs on it. It's got a microcontroller on it, probably some DDR memory. The form factor itself is a 6x9 card. That's called a VPX form factor, and it's pretty much the default de facto Department of Defense form factor and connector that is able to withstand, that connector is able to withstand in that form factor significant ruggedization of fielded systems. But back in 2013, we came up against a very significant challenge that I can't talk about here. We were capturing a lot of data, as I mentioned, hundreds of gigabytes of data per second. The problem with that is we were trying to store a portion of it, and we were trying to store about 3 gigabytes per second. If you think about what 3 gigabytes per second is, DVDs, DVDs are 4.7 gigabytes of storage. So we were doing approximately a DVD of data every second and having to store and maintain that. But at the exact same time, we were kind of manipulating data and monitoring data and making decisions on that data. So that much data, a DVD holds a 2-hour movie. Like that's a lot of data for 2013. We had, and this was a battery powered system. One of the solutions, the knee-jerk solution is, well, you go get a RAID system. You go buy a bunch of hard drives. So that's what servers are. You get a RAID controller, buy a bunch of hard drives, a bunch of parallel fiber optic links, and you're able to store that. Awesome. If you've got a 19-inch rack, if you've got 250 watts of power to spare, if you've got all the, you know what I'm saying? Versus that card that I'm showing, we created, and I'm calling it. It was one of the first, they're common now. PCI Express drives are more than capable of storing data at 6 gigabits per second, which is around 1.5 gigabytes per second. We created a custom SSD, a solid state drive, because out of necessity, we needed something that was low power. We needed something that was in that form factor. We took a RAID, 19-inch rack, freaking giant box, and we took that capability that was, like I said, 300 watts in this physically large, and made it fit into that card, that form factor of a card, 6x9 card. And that was an incredible accomplishment working with the firmware designer who created his own, how I'm going to encrypt. We had to do real-time encryption on this, how I'm going to do error correction. There's all kinds of things that go into an SSD ASIC that we implemented within an FPGA. And we bought, let's see, what was it? 32 2-terabit NAND chips, raw NAND chips. And we connected it all up. And I remember the architecture that we put together. And I said, dude, this is never going to work. Like there's so much, like we were inventing an SSD that could handle gigabytes of data at a time, when SSDs at the time were at best 500 megabytes per second. So I always go back to that, and I remember powering it up. I remember doing the first complete write of the thing. We wrote, it was a total of 4 terabytes of data. We wrote those 4 terabytes in about 8 minutes, which is bonkers. That's a lot of data. Like I have an NAS at home, and I've probably got 16 years of home movies in it, and I've only used 1.5 terabytes of data of HD movie. So we wrote 4 terabytes of data in about 8 minutes, and we read it all back, and we had 0 errors. Oh, just like awesome feeling of holy cow, no one has ever done this before. And we were at the cusp, we were at the leading edge of technology because we had a necessity for our application. Super fun, super exciting. And then what ended up happening is you get to this next level of integration. As I was saying, there's a progression of responsibilities. A level 4, level 5, ultimately a level 6 engineer. You're no longer just doing the card design. You're looking at an entire system. And that's what I've got over on the right. I'm looking at an entire system, even a server, data server, and that communication system I was telling you about the Navy. It is multiple CCAs. It is multiple chassis. It is a SATCOM dedicated communication link. It's a storage dedicated communication link. It's a power. We take in raw 50 volts or 100 volts of power, and we have to convert it out to all these other boxes. So you're now talking about an architectural view and an architectural role description that you have to take on as you proceed and grow in your career area. And that's kind of where I headed. I ended up being what is considered an electronics architect subject matter expert. And what that means is I got to work right next to the customer. They have a problem, and I would say, let me get on the whiteboard. Okay, we're gonna need some storage. I don't know what kind. I don't know if it's a RAID system, but there's a box. And I got to that level of abstraction while still understanding the difficulties that I had learned and all the lessons learned from, creating circuit cards, creating flexible tracking, tagging locators. making patentable individual, inductors and transformers, all that fed into my ability to really see a large system and be able to distribute smaller tasking and sizable chunks and achievable tasks to a team. And that, when I look at that and I'm able to reflect on that, I really enjoyed what I've accomplished so far. It's definitely not over. I will say 2021 to present, this last bullet, after about 19 years of having the same boss, he retired and the position was open. And I felt, as usual, as all these other tasks, I never wanted to be a manager. I never thought of myself wanting to be a manager. I love mentoring. I love the interaction that, we're having right now. I've always enjoyed sharing, and I'm passionate about the work that we do. And I wanted to see if I could apply that to the department that taught me everything I know and became a very big part of me. So I found it, a new opportunity to try something very different than doing my typical electrical engineering design. I still very much get to use all those problem-solving skills. I still have to interact with multidisciplined folks. It's a change of pace, and it's another feather, in my opinion, to L3Harris's hat for the ability to say, hey, let's take this very technical, science-focused person. And you know what? He may be, I wouldn't say burnt out, but I was good. I am good at creating systems like these. And I wanted something new. I wanted something challenging, and this position allowed me to do that. And now, I have been stressed like you wouldn't believe. I feel like I'm learning a completely new career in this role. So yeah, that's a lot of yapping from me. I'm not sure where we are at time. Did we go over by a lot? Holy cow, I am so sorry. I do have a microelectronics capability video that I wanted to share with you all. It's out on YouTube. I'll see if we can get you the link. We probably won't show it here, but I do want to open it up for questions. And I want to end on, L3Harris and just engineering as a whole. It is what you want out of it. So please, please, please drive your career, be proactive, be engaging with your leads, with your team members. Let them know what you're interested in. And I will say, I'm a big fan of the folks who are uncomfortable taking an assignment, saying, I don't know if I can do this. And I will encourage you to try. Take that risk, because you won't know what you won't know if you like it until you try it. And that's what I've really enjoyed about my career here, and specifically within our department. So anyway, I'll open it up. Thank you guys so much.
There might have been a couple chats ready for questions.
Are there?
Well, those were my messages, but I know some of the students had to leave to go to class.
Oh, I'm so sorry.
No, that's okay. Is anyone would like to, well, there's a question now. It's a computer science major. What languages does Harris use the most?
We really use every single one that I can think of. And I will say this is my weakest area, but the software engineers that I've worked with typically like to focus on C. We do use C#. Most of our operating systems that we operate on are Linux-based. We customize the Linux operating systems. Oh, things like MATLAB, Verilog, C++. Yeah, like come on over.
Very transferable as well. So these
super come on over. Yeah, MATLAB, Verilog, VHDL, C++, all of those languages are utilized in our systems. And it very much depends on the application. It very much depends on the platform. So it's very difficult for me to say which is the most common, just because I've worked with every single one of those and we've implemented them.
Great. Did anyone want to unmute and ask a question? All right. Well, I will say, Bayardo, I found your presentation really interesting. I'm not technical, so usually I don't enjoy tech talks, and I really enjoyed yours. you made it easy for me to understand the process of what an engineer might experience. And it's clear that you are so passionate about what you do. Jason,
Appreciate it.
did you want to ask something?
Yes, just curious, I'm working on my second degree now. I'm an EET major or EET bachelor's computer science major here at Florida Tech.
Awesome.
I'm just curious how much cross-disciplinary use you guys do use. Like I know your counterpart there is chemical engineer and PCB development,
Yep.
which is pretty cool. Yeah,
Pretty cool.
but I'm also I already feel dumb. But for things like EET and app development on the RF realm, like how much of those do you guys cross flow over?
So when you mean cross flow over, how much do we interact with the other departments?
Yes.
Oh, significant. Again, the way that L3Harris is organized, as I mentioned earlier, functional engineering. So the electrical engineers are in a department. The digital engineers are in a department. The RF engineers are in a department. But what happens is these departments are resources. And as an engineering manager, I am kind of the middleman when it comes to resources. We have resources of chemical engineers, physicists, micropackaging engineers, software engineers within our department of microelectronics. And what we have is on the other side, you've got functional, which I just described, functional engineering departments, and you've got programs over here. And that's what's described within L3Harris as the business side. These programs will come and say, I need someone with MATLAB skills. I need someone with C++ skills. I need someone with C# skills. I need someone who can make a PCB board. I need someone who understands high-speed digital interfaces. And it is our job to then supply and obviously talk to the experts and supply the programs with the right skill sets and the right set of people. So when you join that program, that same program is also going to reach out to the RF and power and analog engineers and say, hey, we're building a complex system like that last example I was telling you about. That was a program of well over 300 engineers. And I was the chief electrical engineer. There was my counterparts. There were chief mechanical engineer and there was a chief software engineer, as well as actually those were the three: chief mechanical, chief electrical, and chief software engineers. Oh, chief system engineer. Between us four, we had hundreds of engineers developing a very, very complex set of hardware, software, and firmware product lines.
Yeah, as a testament to the complexity and difficulty of these customer problems, the teams are forced to be cross-functional, as you have to have, constant streams of communication between these disciplines in order to solve the problem in a schedule-friendly way. So you have to work together, but I think you said EIT or EET and computer science would definitely be interacting in certain cases and different programs across the company.
Yeah, 100%. I mean, this example board that we've got here, I don't do anything before talking to my software counterparts, my firmware counterparts, my mechanical counterparts. And if I'm going to be making a unique layout or board, I'll reach out to Reed and his counterparts and materials and mechanical. We will not successfully complete any programs without very tight interconnected disciplines.
Does that answer your question, Jason?
It did. I think Alexandra has a question now from the chat.
Yep. Let's see. I see your different engineering disciplines, but didn't notice any encompass material and chemical. Are there material science applications in that specialty? I'm assuming between silicon as a raw material to the electrical development. Yes and yes. So we do have material scientists. In fact, I'd say about a third of our department, which is approximately 90 heads. So I'd say around the third, maybe a little less, maybe a quarter, 20 folks are material scientists. And I don't know if you just saw a little screen jump up, but we have a dedicated group of material scientists currently working on silicon MEMS actuators and fabrication of silicon devices. Along with that, we have another group of material scientists developing new techniques for bonding a high quantity of silicon and dissimilar materials layers. So remember, if I, like I mentioned earlier, we're using silicon substrate, not as an active and doping and creating PN junctions and transistors, but we're using them as routing layers. And what we've done is we've been able to create a process that can bond literally tens to 20 layers of silicon, create vias within that silicon. And as I'm assuming you're a material scientist, you're well aware of what happens when you start messing with the crystalline lattice structure of semiconductor materials, the mismatch in CTE, coefficient of thermal expansion between different materials and coatings. We have active programs as well as research and development programs that work in those areas, but will again tie back into, we've got this now interconnect device that will work with the mechanical engineers to package it, the electrical engineers to actually send information across that device.
Yeah, one of the things that I think Alexandria might have caused confusion is there's not a material scientist or chemical engineering job title. But that really is not important because you can be labeled as whatever electrical. For example, we said earlier, I studied chemical engineering at Florida Tech. I'm an senior associate electrical engineer. I would not be able to tell you nearly as much as what Bayardo knows about electrical engineering, but I work on a side of projects that are, sort of adjacent to electrical engineering, doing chemical engineering, doing process development, doing material science work. So the support for the electrical engineering role is why I'm called an electrical engineer. But as a material scientist or chemical engineer yourself, there are places within our specific department and elsewhere across the corporation where those disciplines are definitely needed. And this is a good segue for me to plug L3Harris.com/careers. Check back there frequently. There's new jobs posted all the time. And if you have any other questions that you can think of, or anybody watching this recording after the fact, feel free to email them to university_relations@L3Harris.com so you can get those questions answered. We can stay in touch. Any other questions?
Jason?
No questions.
Okay. Well, you probably have work to do, both of you, but we really appreciate, I thought this was an excellent presentation. I wish more students could have participated because I think it would really help them understand the career path at L3Harris and get them very excited about some of the really cool projects that you were able to work on. As I said earlier, I found it so interesting, and I usually have a hard time with the tech talks because I never understand what they're talking about. If any of you, I know, I guess we just have Jason really still on. We can maybe one of you can send that link to us. We could share it with the students who attended so they can watch the video.
Absolutely. We'll go ahead and do that. I'll forward to Reed and you all.
All right. Wonderful.
I was going to ask Donna if this would be distributed across the student body or through those the different clubs that we were.
We post it. It'll be on our YouTube channel. So what we can do is send it to the student organizations and encourage them to have their members watch it. Maybe that'll be a good something they can do for one of their meetings. I would certainly encourage that.
That's a great idea. Thank you, Donna, for hosting us again.
Thank you.
Go Panthers.
Thank you. And it was great to meet you, Bayardo. I hope to see you again.
Agreed. All right,
Wonderful.
everyone.
Thank
Have a
you.
wonderful day.
You too. Bye-bye.
Bye-bye.